Hello students, welcome to my channel. So till page number 115, arithmetic of integers, I already explained the laws and theorems. That is for exercise 3.3, that means page number 112 to 115 already I explained in previous video. So today we will start from page number 116, that is theorem number 4. Theorem number 4, it is written already on the board. Theorem number 4, there is given for two integers a and b, at least one of which is non-zero. Two integers a and b. A and b both are integers, but one is non-zero. At least one is non-zero. If a is 0, b is non-zero. If b is 0, a is non-zero. Again, there is given one condition. There exists another two integers x and y. X and y also integers. So that GCD of AB is equal to AX plus BY. Greatest common divisor of AB is equal to AX plus BY. A into that integer plus B into another integer. So this is what we have to prove. Now question is that HCF we have got already, that is just related to greatest common divisor here. The name is different only. How do we find out what is called HCF? In division method. We already got it in general maths and in lower classes. Suppose we want to find out the HCF of 15 and 24. We want to find out the HCF of 15 and 20. What do we do? First we will divide by 15, 24. 15 1 is 15, 9. Now we will divide again this one. 9 1 is 9, 6. Again we will divide 6, 9, 6 1 is 6, 3. Again we will divide 3, 6, 3 2 is 6. Remainder is 0 here. So 3 is called HCF. This you know already. That means until we get remainder 0, we will go on dividing back. By remainder we divide the divisor, then again back, again back, again back. So here we have got last non-zero remainder is HCF. This is the HCF. Why this is the HCF? This is non-zero remainder. After that, when we divide again, we get a remainder 0. So this is last zero remainder. This is last non-zero remainder. So this is the HCF. This is the HCF. So by these three, we have divided 6. We have got remainder 0. So this is the HCF. This is the common. This is related to general maths. That I have given the idea to how to find out HCF of two numbers. So this is the division method. We have to go on dividing till we get remainder 0. Once we get remainder 0, we will stop division. Then this divisor will be the HCF, or last non-zero remainder is the HCF. Last non-zero remainder is the HCF. I hope this one you understand. Okay. Now, if b equals to 0, here there is given a and b, at least one of which is non-zero. Now we are taking b equals to 0. Then GCD of a, b will be 0, because in place of b now 0. In place of b now 0. So a and 0, HCF will be, or GCD will be 0. By taking x equals to 1 and y equals to 0, to satisfy a equals to a1 plus 0 comma 0, ax plus by, this type. X is 1. So a into x, 1 plus b is 0. So 0, y also 0, so 0. So if we multiply, or if we do the calculation, a into 1 is a, plus 0 into 0 is 0. So a plus 0 is a. This condition satisfied by x equals to 1, y equals to 0, and b equals to 0. A equals to a into 1 plus 0 comma 0. This is condition. If you do the calculation, you will get back a. Now if here we have taken b equals to 0, now we are taking b is not equal to 0, then a equals to bq1 plus r1, where this one I will explain now. This one already got in previous first theorem. A equals to bq1 plus r1. That means a equals to bq plus r. How it is? A, b, q. This is quotient, this is divisor, this is dividend, this is remainder. If it is divided by 2, 15, if you divide by 2, 7 is 14, remainder is 1. Isn't it? This is A, this is B, this is Q, this is R. So 15 is equal to 2 into 7 plus 1. 15 means what? A, 2 means, sorry, yes, 2 means B, Q, 7 means Q, plus 1 means R. So A equals to BQ plus R. This one already I explained in the first theorem. Now, A equals to BQ1 plus R1. So let us divide 71 by, this is an example, by 15. To show this one, A equals to BQ1 plus R1. R1 is greater than equal to 0 and R1 is less than B. This is what I want to show you. Okay. A. This is A. This is B. Okay. A is dividing by B. Now 15 for the 60. Remainder is 11. So first we will go on dividing. So first question let us take as Q1 and first remainder let us take as R1. Okay, 71 is equal to 15 into 4 plus 11. 71 means A. 71 means A equals to BQ1 plus R1. A equals to BQ1 plus R1, where R1 is greater. Here remainder will never be less than 0. Remainder, if it is divisible, if suppose here 60, 15 plus 60, 60 minus 60, 0. Remainder may be 0. Remainder will be always greater than 0. Remainder may be 0, may be greater than 0. And remainder will never be greater than 15. 11, here we cannot get a number greater than 15. This remainder will be always less than this divisor. That means remainder R1 is less than B. This remainder, this is common sense. This is common to all of us. We know that. Now, this one I have explained here. Next, B equals to R1 Q2 plus R2. This one I will explain now. While just previous 2 minutes ago, I have shown you how to get remainder by division method. So by remainder we will divide this divisor. So 11 we will divide 15 now. 11 1 is 11. This is 4. Remainder is 4. Okay. What is 11? I have put bracket here R1. So let us go to R1. What is 15? B. Let us write B. Now in first division, first quotient is Q1. So second division, in that second step of division, second quotient will be Q2. If it is Q1, this will be Q2. Next will be Q3. Like this. First remainder is R1. Second remainder is R2. We will go on dividing like this. If first one is 11 and that is R1, so 4 cannot be R1, no, because 11 and 4 different number. 4 is Q1, so 1 cannot be Q1. So 4 is taken is Q1, second one is Q2, third one we will take Q3. First remainder is R1, second remainder is R2, third remainder we will put R3, like this. So this one I want to show here. B equals to 15 equals to 11 into 1 plus 4. B equals to R1 into Q2 plus R2. B equals to R1 into Q2 plus R2. This one I hope you understand. Third one now. Now according to rule, by this one we will divide this one again. 4, 11. Okay. By 4 we will divide 11 again. So here also one time only 4 1 is 4. Sorry, 4 2 is 8. 4 2 is 8. Remainder is 3. Now what is 4? R2. What is 11? R1. First quotient is Q1, Q2. This will be Q3. First remainder R1, second remainder R2, third remainder is R3. So 11 is equal to 4 into 2 plus 3. R1 is equal to R2 plus Q3. R1 is equal to R2 plus Q3 plus R3 plus R3. This one also I hope understand. Like this again. By 3 we will divide this one 4 again. 3, 4. 3 1 that 3. Remainder is 1. Remainder is 1. Q1, Q2, Q3, Q4. R1, R2, R3, R4. What is 3? R3. So let me write R3 here. What is 4? R2. 4 is equal to 3 into 1 plus 1. R2 is equal to R3 into Q4 plus R4. R2 is equal to R3 into Q4 plus R4. Like this we can go on dividing until a remainder of 0 is reached. We will go on dividing till we get remainder 0. That will be called, that is called GCD or HCF in common language. HCF. So like this we will go on, so on. We will go on dividing until a remainder of 0 is reached. I hope you this sentence you understand. Because last 5 minutes ago I have explained how to get a remainder 0 and which will be the GCD. Now R1 equals to A minus BQ. This one we have already found here in previous video. A equals to BQ1 plus R1. R1 equals to BQ1 will go that side. So this is what just repeated here. A equals to BQ1 plus R1. So R1 equals to A minus BQ1. Okay. Then R2 is equal to B minus R1 Q2. B equals to R1 Q2 minus R2. This one is there here. B equals to R1 Q2 plus R2. So R2 is equal to R1 Q2 will go that side. B minus R1 Q2. B minus R1 Q2. So B minus as it is. In place of R1, putting the value of R1. R1 is A minus BQ1. So A minus BQ1. Q2 as it is. Now just multiplying A into Q2, A Q2, BQ1 Q2, BQ1 Q2 minus plus. So R2 is equal to minus AQ. Here I have written B and BQ1 Q2. B is taken common. So 1 plus Q1 Q2. This is like AX plus BY. AX plus BY. Just I have put the symbolically AX plus BY. Now now this is something here wrong. Okay. N plus 1, N plus 1. Okay. Now look here. R n minus 1 equal to R n Q n plus 1 and R n plus 1. So let me write from here R2, R3, R4. R2 equal to R3 Q4. R3 Q4 plus R4. This is what we have got. Then R3, R4, like this we can go on adding. This one I have shown in previous page. So that means how it is. If 3, 2, 4, 4. If it is R3, this is if it is R3, 2 becomes 3. 3 becomes 4. Q becomes 5. R becomes 5. So how do we understand? 3, 2, 4, 4. 4, 3, 5, 5. That means this one, look here, 3 minus 1, 3 plus 1, 3 plus 1. I hope you understand. 3 I have put as it is 3. This 2 means 3 minus 1. 4 means 3 plus 1. This 4 means 3 plus 1. Okay. 4 minus 1. 4 plus 1. This is 4 plus 1. If it is n, if it is 4, here 4 minus 1. If it is n, then R minus 1. I hope you understand. Let me explain again. 3 will be 3 minus 1. 4 will be 4 minus 1. So n will be n minus 1. R3Q4. For Q, 3 will be 3 plus 1. 4 will be 4 plus 1. N will be n plus 1. Plus R5, R4. This one and this one same. This one and this one same. 3 plus 1, 3 plus 1. So n plus 1, n plus 1. This is what I have written here. This one. This one I hope you understand. This one from where we have got? From this one. R1, R2, R3, R4, Rn minus 1. Rn minus 1 equals to, this is the condition we have got from here. This, if you have understood, this one you will understand surely. So this is the non-zero remainder. This one. Why this is non-zero remainder? I will show you the example here. This one, let us divide again. 1, 3. 1 1 is 1. 3 minus 1, 2. Again, 3 1 is 3. 41 minus 3. 2, 2, 11, 4, 3, 3, 4. So 1, 3. Sorry, it is somewhere mistake here. Okay. Now by 1 we will divide 3. By 1 let us divide 3. 1 3 is 3. This is 0. 0 remainder. This is non-zero remainder. This is non-zero remainder. This is 0 remainder. Look here. R3. R2 is equal to R3 Q4 plus R4. So R3 is non-zero. This is R3. Now this R3 will go here. How do we get here? R3 means this one 3. This is R3. Here it is written in the next video, the next page. Rn. Rn is non-zero remainder. Here whatever we get, this is non-zero remainder. Non-zero remainder. This is non-zero remainder. This is non-zero remainder. R4, R3. R4, R4, sorry, R4, this one, R3, Q4, R3, Q4, this is R2. Next, what we will write? R3 is equal to R2, R4, Q5 plus R5. So R4 is the non-zero remainder. This is zero remainder, this is non-zero remainder. R4 is non-zero remainder. This is n. R4 means n. This is n minus 1. 4, 4 minus 1. This is R4, non-zero remainder. This is zero remainder. This is R5. This is zero remainder. R4 means this one. If it is n, this is n minus 1. That means n is non-zero remainder. There is no zero. This is non-zero remainder. This is last remainder. So that this can be GCD. HCF means. So I hope you understand. Rn is non-zero remainder. Now, this condition, how can you write in terms of n? R2, I am writing Rn equals to minus A. Q2, if it is 2, here also 2. If it is n, so here also n. Plus B, 1 plus Q1, Q2. Q1, Q2, Qn, n plus 1, 1, 1 plus 1, 2, 2 plus 1. So n, n plus 1. This is the condition, this is the term I have written again here. So Rn is equal to, this A I have taken separately, minus Qn taken inside. B, this one keeping as it is. This one is taken as Ax plus By. What is x? X equals to minus Qn. What is y? 1 plus Qn, Qn plus 1. So GCD of AB equals to Ax plus By. Rn means, what is Rn? Rn is the non-zero remainder. When we get non-zero remainder, this is the GCD. GCD of 15 and 71 is, when we get 15 and GCD of 15 and 71, when we get non-zero remainder. This is the remainder. Sorry, this is the HCF or GCD. When we get GCD 3, when we get a last non-zero remainder. This is A, this is B. Sorry, this is A, this is B. A, B. GCD of AB is 3. When do we get 3? When we have got last remainder non-zero. This is non-zero. And that is Rn. Rn is non-zero remainder. When we get Rn, Rn is non-zero remainder. When do we get Rn? When we get a GCD. So GCD of AB will be AX plus BY. This is what we have to prove. This is what we have to prove, AX plus BY. So in terms, just x equals to minus qn, 1 plus q1, qn plus 1. This is integers, just integers, any number. Definition 6, relatively prime integer. Two integers A and B, both of which are non-zero, are called relatively prime or mutually prime to each other. That means GCD of AB will be 1. That is common sense. HCF of 5 and 3, 1, because both are prime numbers. 5 will be 1 into 5, 3 will be 1 into 3. Common is 1. So HCF is 1. That you know. Why HCF is 1? Because both are prime to each other. Both are co-prime. That means both are prime numbers. When we want to find out HCF of two prime numbers, we will get always HCF 1. Same thing here also. GCD of AB will be 1 when prime, mutually prime to each other. 4 and minus 3. So this one example, you understand that. So both are called relatively prime or mutually prime to each other. Even if it is 4 and 5, then also 1. Both may not be prime. 1 may be prime, 1 is not prime. So then also we will get HCF 1. That is GCD 1. So here GCD of my 4 and minus 3, 1. In the same way, 27, 32, 1 minus 4, relative prime pairs of 4. Relative prime means both may not be prime. Mutually prime means both are prime to each other. So as we know, HCF of two prime numbers or relative prime numbers will be always 1. Same thing here also. Theorem number 5 is very important. Theorem number 5. Two integers A and B, both of which are non-zero, will be relatively prime to each other if and only if there exist two integers x and y such that ax plus by equals to 1. So first of all, what we know? A and B prime. And which are non-zero. If and only if. Here if and only if written means we have to prove both sides. If A and B are two integers, A and B are prime to each other, then ax plus by equals to 1. Again conversely, if ax plus by equals to 1, we have to prove A and B are prime. Conversely. So here it is given in the book, proof is given. Let A and B be two relatively prime integers, so GCD of AB equals to 1. This one we have got already. GCD of AB will be 1. Greatest common divisor of A and B, because both are prime, so we will get 1. By theorem 4, we can find two integers x and y such that GCD of AB equals to ax plus by. So theorem number 4 is applied here. Theorem number 4. GCD of AB equals to ax plus by. This is theorem number 4 for any two integers A and B. For any two integers A and B, GCD of AB equals to ax plus by. In place of GCD of AB, 1 is written because GCD of AB 1. So 1 equals to ax plus by, finished. Ax plus by equals to 1, it is proved here. Conversely, ax plus by equals to 1 given, we have to prove AB prime. So conversely, let 1 equals to ax plus by or ax plus by equals to 1. So GCD of AB equals to D taken, left taken. GCD of AB taken D. That means by D A can be divided, by D B also can be divided. Then only you can get HCF of 4 and 6 2. HCF of 4 and 6 2. So by 2, 4 is divisible. By 2, 6 also divisible. Same thing. GCD of AB is D taken left. So by D, A is divisible. By D, B is also divisible. So that is why then D divides A, D divides B. D divides A, D divides B. D divide AX plus BY. This one is theorem number 37. Theorem number 37 is there in page number 113. Page number 113, 37, theorem number 37. If A divides B and A divides C, then A divides BX plus CY. A divides B, A divides C. If A divides C, sorry, A divides B, A divides B, A divides C, then A equals to BX plus CY. A equals to A divides BX plus Y, sorry. A or divides BX plus CY. A divides B, A divides C, then A divides BX plus CY. With B one integer, with C one integer, and addition will be also divisible. This is the theorem. 3 number 7. 3 number 7. So here D divides A, D divides B. So D divides AX plus BY, BX plus CY. With B, with this one X comes, with this one Y comes. So with first one X comes, with second one Y comes. So D divides AX plus BY. AX plus BY, this is 1. So D divides 1. If D divides 1, D equals to 1. D divides 1, D will be equal to 1. 1 is divisible only by 1 only. 1 is not divisible by any other number except 1. So if D divides 1, so D is surely 1. So GCD of, what is D? GCD of AB is D. So what we have got, D equals to 1. So GCD of AB equals to 1. So when GCD of AB equals to 1, in other words, A and B are relatively prime. Same thing I have done here also. Same thing. So just little different I have written to make you understand. You can note it down by making the video pause. Corollary number 1. If GCD of AB equals to D, GCD of A by D equals to B by A by D, B by D equals to 1. GCD of AB equals to D. Then GCD of A by D, comma B by D equals to also 1. We have to prove that. So if GCD of AB equals to D, this is given. If it is given, then we can write according to theorem AX plus BY equals to D. This one already got in previous theorem, theorem number 5. GCD of AB equals to D. GCD of AB, we have got in theorem number 4. GCD of AB is equal to AX plus BY. Here GCD of AB is given D. So D equals to AX plus BY. That is what I have written here. I hope you understand. So AX plus BY equals to D for some integers X and Y. So if AX plus BY equals to D, so D divides A, D also divides B. Surely. This one already I have explained. So D divides A, D divides B. So that A by D and B by D are two integers. Look here. D divides A, D divides B. This one we can write in fraction now. D divides A. 5 divides 15. How can we write in fixed fraction? 15 by 5. This one you understand. So D divides A. We can write A by D. This one we can write B by D. This is what here written. A by D and B by D are two integers. If D divides A, if D divides B, we can write, we can express this one as this one as this one. So, if AX plus BY equals to D, if AX plus BY equals to D, dividing, okay. AX plus BY equals to D. This one we have got. So we will divide by D. Okay, left hand side, right hand side, we are dividing by D. So what? A by D x plus B by D y equals D by D 1. So A by D x plus B by D y equals to 1. By theorem 5, A by D and B by D are two related things. When we get 1, A by D x, B by D y equals to 1. When do we get 1? According to theorem number 5. Theorem number 5, just previous page we have got theorem number 5. When ax plus by equals to 1, that means GCD of AB equals to 1. Okay. Theorem number 5. If A and B are a prime number, then ax plus by equals to 1. That means GCD of AB equals to 1 when ax plus by equals to 1. So ax plus by, this just take as a, this is take as b. So ax plus by equals to 1 when this, the GCD of this and this is A, this is B. GCD of A and B 1. So GCD of A by D, B by D 1. Corollary number 2. If A divides C, B divides C, then GCD of AB and 1, this is and, then AB also divide C. A divides C, B divides C, so AB also divides C. And GCD of AB 1. GCD of AB 1 means AB prime. When do we get GCD of AB 1? When AB both are prime. Okay. Look here. 5 divides 15. 3 also divides 15. So AB, this is A, C, this is B, C. A divides C, B divides C. 5 3 are 15, also divides 15. 5 3 are 15 means what? A into B. 15, this 15 means what? C. So AB also divides C. Because 5 and 3 both are prime. This is just example I have given here to make you understand. So since A by C, A divides C, so C equals to AR. B divides C, so C equals to BS. Just R and S just simply taken as integers, any integers R and you can take X, Y also, you can take PQ, no problem. So GCD of AB, there is given GCD of AB equals to 1. GCD of AB equals to 1. So therefore what? AX plus BY equals to 1. AX plus BY, because theorem is there. Just we have got previous page theorem. If GCD of any two number is 1, that means AB prime. So AX plus BY also 1. AX plus BY also 1. Now we will multiply both sides by C. Why we are multiplying by C? Because we have to prove AB divides C. So CAX plus CBY equals to C. CAX, CBY, C into 1, C. So what do you get? CAX plus CBY equals to C. Now, in place of C, we will write AR. In place of C, we will write A. C is BS, sorry. Here something CAR, CBS. Okay. In place of C, we will write now BS. BSAX. In place of this C, we will write AR. ARBY equals to C. Now, BSAX, ARBY. Now we will write BS AX AR BY equal to C. Now we will write AB. At least we can actually from here only we can take AB common. AB common. AB taken common. What is left here? SX plus RY equals to C. Sx plus ry any integer. AB into any integer equals to C. Look here. AB into something equals to C. AB into 1 suppose equal to C. This is any integer 1. I have taken 1. No problem. No. So AB divides C. Look here. C equals to AB. So AB divides C. C equals to AB. AB divides C. C equals to AR. C equals to AR. A divides C. Look here. C equals to AR. From where we have written A divides C. A divides C. A divides C. With A there is one integer. Okay. AB into this one just think as P. Suppose P. AB P equals to C. AB P equals to C. This one AB A. This one P. This one just think as A. A into P equals to C. So A divides C. This one divides C. A means AB. So divides C. This divides this. This divides this. Just you have to make it understand. Just you have to understand what I am going to write. AR equals to C. So A divides C. If I write AX R C, that means AX divides C. I hope you understand. Again, C equals to A X plus Y into R. This one just think as A. C equals to AR. So A divides C. What is it? A into X plus Y divides C. Hope you understand. Theorem number 6. Euclid's lemma. If A divides BC, A divides BC, GCD AB equals to 1, then we have to show A divides C. If A divides BC and GCD of AB 1, that means AB prime. 1 means AB prime. So we have to prove A divides C. For any integers X and Y, any two integers AX plus BY equals to 1. Why? Because GCD of AB is equal to 1 according to theorem AX plus BY equals to 1. So here also we will multiply by C both sides. CAX CBY equals to C. Then C is multiplied. So here you can put bracket. Here you can put bracket like this. This is what done here, CAX plus CBY. Given that A divides BC, so A divides AC also. How this one came? Listen. This one is given. A divides BC, it is given. Obviously, A also divides AC. How? Let us see 1 divides C. 1 divides C. Both sides multiplying by A. A into 1 divides A into C. Okay? A into 1 is A. A into C is AC. I hope you understand. Since A divides BC, obvious that it is common that A also divides AC. This is what I have explained here. If 2 divides 6, both sides if we multiply, 2 divides suppose 8. 2 divides 8. So if we multiply both sides 2, that means what? 4 also divides 16. 2 divides 8. Both sides we are multiplying by 2. 2 into 2, 4. 8 into 2, 16. So 4 also divides 16. So same thing here. So A divides AC. Now therefore, A divides AC means A divides ACX plus BCY. This one has come from this theorem. This one I have written here, theorem number 37. Look here, A divides B, A divides C, then A divides BX plus CY. With this one, X will come. With this one, X came. With another one, Y came. ACX, BCY. ACX, BCY. A divides B, A divides C. A divides B, A divides C. A divides BX plus CY. Okay? This one just think as B, this one I just think as C. A divides B, A divides C. A divides A, BX, BX, BX plus CY. B means AC, C means BC. I hope you understand. So that means A divides C. That means A divides C. How do we come to know A divides C? A divides AC, A divides BC. Look here, A divides AC. So A divides C also, because this is multiplication now. So look here, if 5 divides 2 into 5, or 5 divides 10 into 20. 5 divides 10 into 20. So 5 divides 20. A divides C. So A divides C. 3.4.3 Euclidean algorithm. GCD of two integers can also be computed by repeated use of division logarithm. This method is called Euclidean algorithm. Repeated division. Repeated division, that is called Euclidean algorithm. Let us first consider the following lemma. Lemma 1. Lemma 1. Okay. Here, this one is given in the book actually. Okay. A equals to BQ plus R, GCD of AB equals GCD of BR. GCD of two integers can also be computed by repeat or division. The method is called Euclidean algorithm. This one you will see yourself, but I will show you one. This one you will see yourself, then you may understand. But this one, let us understand this one. Lemma 1. It is given in page number 119. Page number 119, lemma 1, that is given in the book, which you can understand. But this one, you see, if A equals to BQ plus R, this one you understand, I think. GCD of AB equals GCD of BR. Look here. A equals to BQ, this one A, B, Q, R. Divisor, dividend, quotient, remainder. Then what happens? GCD of AB is equal to GCD of BR. GCD of AB equals to GCD of BR. Try to understand what is the theorem. Now look here. 5 and 10. 5 2 10. 0. Okay, not correct this one. So if when we do a division, so in the first page, today's first page, we have done 15 and 71. 15 and 71, we have got 3 as HCF, that means GCD. 15 and 17, two numbers, and we have got what is called GCD 3. Yes, we have done 15 and 71. GCD we have got 3. Okay, and remainder what we have got in that page, remainder we got remainder is 1. Remainder we got 1. No, this leave it. This will be confused for you, so just see this one. A equals to BQ plus R, then this you have to prove this one. Let GCD of AB equals to D and GCD of BR equals to E. For this one we have taken D and for this one we have taken E. Just taken let. By definition A equals to BQ plus R. Okay. If K be the common divisor of B and R. If K be the common divisor of B and R. Common divisor. That means 15 for 15, 3 and 5 common divisor. For 15 and 25, for 15 and 25 common divisor is 5. Because by 5 we can divide 15, by 5 we can divide 25. Like B and R, common divisor is taken K. Let K be the common divisor for B and R. So if common divisor, what is the common divisor? K. So by 5 we can divide 15, by 5 we will divide 25. K divides B, K divides R. K divides B and K divides R. I hope you understand. K also divides A because A equals to BQ plus R. Why? Look here. If this one and this one both are divisible by K, so by K we can divide this one also. I will show you one example. 15 and 25. What is 15? A equals to BQ plus R. A equals to BQ plus R. What is B? 15. What is R? 25. Q. What is K? K is suppose 5. So by 5 15 is divisible. By 5 25 is divisible. So K also divides A. Whatever we get, look here, 15 into 2. Suppose Q is 2. 15 into 2 is 30. 30 plus 25 is 55. So 55 is divisible by 5. What is 5? 5 is K. 5 is K. By 5 15 is divisible. By 5 25 is divisible. 15 to the 30. 30 plus 25 is 55. What is 55? A. So by 5 55 is also divisible. So K also divides A. What is A? 55. Therefore K is common divisor of A and B. Common divisor of A and B. Look here. What is A? 55. What is B? 15. 55 and 15. 55 is equal to 5 into 11. And 15 is equal to 5 into 3. So 55 is A. 15 is B. So 5 is K. 5 is common divisor of 55 and 15. K is common divisor of A and B. This is what I have done. Therefore, K is common divisor of A and B. Conversely, this one you have proved now. What we have proved? If GCD A equals to BQ plus R, then K is common divisor of A and B. We have proved. Here, K. Now, let K be the common divisor of AB. Conversely, we will get. Then A equals to BQ plus R. K divides B, K divides R. K is common divisor of A and B. So, A equals to BQ plus R. So, by K, B can be divided, R can be divided. Because common. So, B will be divisible by K, R will be divisible by K. So, K divides B, K divides R. Thus, K is common divisor of B and R also. B and R. So, GCD of AB and GCD of BR equals GCD of AB. Whatever we will get same thing for GCD of BR. Illustration. This one is an example, so you will understand this now properly. Applying division algorithm, A equals to 57 equals and B equals to 12, we have 57. Now this one just illustration. Page number. Okay. Applying division algorithm, A equals to 57, B equals to 12, we have 57. Okay. So 57 is equal to 12 into 4 plus 9. How? 57, if we divide by 12, 57, wait, 57, 12 4 are 48. This is 9, remainder is 9. So 57 equals 12 into 4 plus 9. 12 into 4 plus 9. So here Q is, this is Q, this is R. Okay. Means A equals to BQ plus R. Q is quotient, R 9. So this one I hope you understand. So GCD of AB is equal to GCD what, 57 and 12. What we have got? 3. We have not found here. Let us find out the GCD of 57 and 12. 57 and 12. 12 4 the 48, 9. By 9 we divide again 12. 9 1 the 12. 9 1 the 9. 3. By 3 we divide again 9. 3 3 the 9. 0. 0. So this is the GCD. This is GCD, or this is the GCD. Last non-zero remainder will be GCD. Okay, or this one is last divisor is GCD. When we get 0 remainder, last divisor is the GCD. So GCD is given 3. Now GCD of BR, which is B, which is R. This is B. B is 12. R is 9. Let us say where we get 3 or not. GCD of AB we have got 3. GCD of BR we get 3 or not. 12 and 9. Okay, by 9 we divide 12. 9 1 are 9. 3 by 3 we divide again 9. 3 3 are 9. 0. So this is the GCD. So this one also. This is A, B, this is BR. Whatever we get GCD of AB, same thing we will get GCD of BR. That means GCD of AB and GCD of BR always equal. Just we have proved here. This is what we have done. You will do this one yourself, then you will understand. The foregoing lemma will be used to calculate the GCD of two non-zero integers. GCD of two non-zero integers. This one actually this is not required. GCD of AB is equal to GCD of A minus B is equal to GCD of minus A minus B. This is what. It therefore makes no difference if we assume both A and B positive, negative, no difference. That is what it means. This is what only you have to remember. This is not. This one again you can yourself can do 51 and 18. So 51 and 18 you can do yourself now. Okay. Okay, let me do 50. Let us consider 2 into 51 and applying the operation of long division repeatedly. We have this one. 51 and 18. 18 is smaller. So 51. 18 1 the 18 3 the 18 2 the 36. 15 is the remainder. So how can we write this one? 51 is equal to 18 into 2 plus 15. This is step number 1. Oh. Now GCD. GCD of AB is equal to GCD of BR. This is what we are going to add. AB means AB 51 18. BR 18 comma 15. I hope you understand. Second step now. By 15 we will divide 18 now. By 15 we will divide 18. 15 1 is 15. 3. Okay. So what you will write? 18 is equal to 15 into 1 plus 3. So A B, this is R. Okay. So GCD of 18 comma 15 is equal to GCD of BR 15 and 3. 15 and 3. This is second step. 15 and 3. Second step. Third step. By 3 we will divide 15 now. By 3 we will divide 15. 3 5 are 15. 0. That is 15 is equal to 3 into 5 plus 0. Now what we will write? GCD of AB 15 comma 3 is equal to GCD of BR 3 comma 0 is 3. GCD of 3 comma 0 3. So finally what we have got? GCD 51 comma 18 is equal to GCD of, look here, 51 comma 18 equals to this. This one came here equals to this. This one came here equals to this. This means this. This is what written step by step here. GCD 51 18 18 15. 18 15 equals to 15 comma 3. 15 comma 3 is equal to GCD 3 comma 0. GCD 3 comma 0 equals to 3. This one, whatever written in the book, so I have explained it. Now this one we have to do in short method. This one we have to do in short method. So this one you may not understand. So I will make you understand. Look here. 51 and 18 it was there. So look here. 51 and 18. 51 and 18. 18 2 are 36. 5 15. Remainder is 15. So by 15 we will divide again 18. 15. Okay, this 2 we can write this side, no problem. 2. 18 2 are 36. Remainder is 15. 15 came back here. 15 1 are 15. 15 1 are 15. Wait, I will show you in different way, then you will understand this one. 51 18. 18 2 are 36. 15 18. 15 1 are 15. 3 15. This one I think you have got in general maths. Long division, short division method. So what is the HCF? We have done HCF. This is the HCF. Here it will be called GCD. Okay. Here it is shown like this. This same thing we have done here, it's still different. 18 51. 18 2 are 36. 15 1 are 15. 3 this way. 3 then 3 5 are 15. 0. Look here. Okay. Now this one, look here. This one first question Q1. This is second question Q2. This is third question Q3. I hope you understand this one. First what we have done, 18 into 2 is 36. First question. 15 1 are 15. Second question. 3 5 are 15. Third question. So this is first remainder. This is second remainder. And this is third remainder. This is what written here. So I hope you understand this one. So this one short method. So this is the GCD. This method, if you have understood, this one also understood. No? Let me explain again. 18 2 are 36. Remainder is 15. 15 1 are 15. 8 minus 5 3. 3 5 are 15. Finish. Theorem number 7. Theorem number 7, let me do here. This book one, it is little difficult, little complicated. So I will do now myself so that you can understand. Theorem number 7. If A and B are two positive integers, then GCD of K equals to K into GCD of AB. That means GCD of 5 and 10, 10 and 15, GCD of 10 and 15 is equal to 15 and 25. 15 and 25. Then 5 into GCD of 3 and 5. This way. This is K. This is the meaning. Okay. Let GCD of AB is D. So D divides A, D divides B. This is what written here. If D divides A, so A equals to D into something, integer. If D divides B, B equals to D something. So here something is taken X, here something is taken Y. This is constant positive. Okay. Such that GCD XY equals to 1. Means X and Y both are prime. X and Y co-prime. Prime to each other. We have taken, this is let. Multiplying A and B by K. Multiplying A and B by K. Here multiplying both sides by K. K equals to K dx. K equals to K dx. KB equals to K dy. KB equals to K dy. K and KB are multiples of K. KA equals to something. KB equals to something. This equals to K into something. This equals to K into something. So by K, this is divisible. By K, this is also divisible. That is why K and KB are multiples of K. 15 equals to 3 into 5. 18 equals to 3 into 6. So this is K. K equals to K into something. KB equals to K into something. So whatever we get here, K into something. So by K it will be divisible. So K and KB are multiples of K. Then GCD of K equals to KB equals to GCD of dx dy. Dx dy from where it came? A means dx, D means dy. GCD of A and B. A is dx, B is dy. GCD of K and KB. K and KB. Look here, K and KB. K means K dx. K dx. K dy. So K GCD of dx and dy. Short form. Number 1. This is number 1. Now we know that GCD of dx dy is d times the GCD of x and y. We have got this one. GCD of dx dy is d times the GCD of x and y. X and y are co-prime, so GCD of xy equals to 1. So GCD of dx dy equals to d GCD of xy. D into GCD of xy. GCD of xy is 1, so d into 1 is d. So GCD of KB is equal to GCD of K into GCD of AB. GCD of K into KB, GCD of dx dy. GCD of dx dy we have got d. So GCD of dx dy we have got d. D, no? So GCD of KB equals to K into GCD of AB. GCD of AB is GCD of AB is D. GCD of dx dy also D. That is why these two are equal. 3.4.4 lowest common multiple. That means it is like LCM. Now we have done LCM. LCM we are familiar with LCM. We have got in general maths. So the lowest common multiple for two non-zero integers A and B is positive integers M, such that B is the positive integer M. A and B. Lowest common multiple is M. So then number 1, A divides M, B also divides M. Number 2, for some positive integer C, A divides C, B also divides C, then M will never be greater than C. M is smaller than equal to C. This one you can do by example. A and B. Look here. 15 and 25 LCM. We will find out LCM. 15 is equal to 3 into 5. 25 is equal to 5 into 5. So LCM, first common, 5, then 3 into 5. 5 3 is 15, 15 5 is 125. 125 is the M. This is A, this is B. LCM of A and B is M. LCM of A and B is 125. There is another number, C, which A divides C, B also divides C. Another number. A divides C, B also divides C. Another number. So 15 and 25, 1 to 50. 15 to 50. Suppose 625. 625. 625. 15, 65. Okay. Some example, it will take time to think and number. So this is a C. C is a number which divides by A. C is a number which divides by C. So in that case, M will be M. Whatever number we take, that will be smaller than equal to C. That means LCM will be smaller than that number. That means if we take a number, big number, by 15 you can divide that. By 25 also we can divide that. We can get one more example. Illustration. Here it is given. Let us consider A equals to minus 12, B equals to 30. Positive multiples of A equals to minus 12. And this one, similarly this one. Now, lowest common multiple is 60. It is to be noted that AB is okay. Minus 12 and 30 taken. So for minus 12, 12 1 is 12, 12 is 24, 36, 48, and 60, 72, like this it is written. For 30, 31 is 30, 60, 90, 120, 150, like this, go on writing. Now common positive multiples of A and B are 60. 60, no? 60, then next we will get 60, next we will get 120. We will go on getting, no? See, 60, 60, then 120, 120, common, writing common. Okay, common multiples. So what is the LCM, lowest common multiple? We will go on getting, but what is the common? Lowest is 60. So LCM will be 60. Do you understand that? Common multiples of 12, multiples of 12 we have written, multiples of 30 we have written. We have taken common numbers. Among the common numbers, 60 is the lowest common multiple. So this is LCM. It is to be noted that LCM of AB, 1230 minus 1230 is mode of AB. Mode of AB means minus 12 and 30, whatever we get, that means this is 60. Okay, this is 60 or whatever it is, we will get always positive. So whatever LCM, HCF, always we get positive. That's what it is a meaning. Mode means always positive. Theorem number 8. Okay, theorem number 8. For any two positive integers a and b, GCD of AB, GCD of AB into LCM of AB is equal to AB. This one I will show you an example with general maths like HCF and LCM. HCF and LCM. HCF of 8 and 12 and LCM of 8 and 12 always equal. This is what here given. HCF of AB into LCM of AB equals to AB. Look here. HCF of, let us find the HCF of 8 and 12. HCF of 8 and 12 will be 4. Is it not? HCF of 8 is equal to 2 into 2 into 2. 12 is equal to 2 into 2 into 3. So 2 into 2 is 4. That is HCF is 4. LCM will be, this is HCF, okay, this is LCM. 4 into 2 into 3. 4 to the 8 is 24. So LCM is 24. So what is the formula we got in general maths? HCF into LCM is equal to multiplication of both the number. HCF is 4, LCM is 24, and one number is 8, other number is 12. HCF into LCM is equal to the sum multiplication of both the numbers. Same thing. HCF into LCM is equal to multiplication of both the number. 4 into 24 is 96. 8 into 12 also 96. This is what given. This one in easy language. This one related to general maths, which we got already in general maths. This one you have got that experience of having this. So if you have understood this one, then you will surely understand this one. So here it is done like this. This one you will note down so that you can understand. So I am going to rub it, erase it, so that we can do the sum easily. Now GCD of AB. GCD of AB is taken D. GCD of AB is taken D left. So D divides A, D divides B. This one is common. This one you know already. So D divides A, D divides B. So A equals to dr and B equals to ds. R and S any integers that we can take. X, Y we can take, no problem. P, Q we can take any integer. So A equals to dr, B equals to M. M is the LCM. We have got already in previous theorem. M we are taking left AB by D, because M we know already got in theorem. D divides A, D divides B. M is the LCM, which will be equal to AB by D. AB by D. This is just LCM. We are taking let only. No problem for this. M. Now A equals to dr. In place of A, dr written. Then B by D. Okay. Equals to what? D cancel RB. Again, M equals to AB by D. Now we will write in place of B, ds. D cancel. This is AS. So M equals to RB, M equals to AS. M equals to RB, M equals to AS. So M is common multiple of, look here, M equals to RB, M equals to AS. So M is common for A and D. M is common multiple of A and D, because R into B, A into S. R and S any integer. So M equals to, look here, 15 is equal to 3 into 5. And 30 is equal to 6 into 5. So this is this one like this. So this one and this one common. Okay. So M is equal to RB, M equal to IS. So M is common multiple of A and B. Here. So M is common multiple. Now let us take C be another positive integer which is also common multiple of A and B. C is another common multiple. C is another common multiple of A and B. So A divides C and B also divides C. A divides C, B divides C. So C equals to A P. You can take no problem. Then C equals to B Q. Here taken U and for some integers, any integers, P and Q, any integers. So D equal to what is D? D equals to GCD of AB. D is equal to GCD of AB. D equals to GCD of AB. This one we know AX plus BY. This one already got in theorem. AX plus where X and Y two integers. Theorem number 4. Now C by M equals to C by, like here M we have taken AB by D. Here C by M equals to C by C and M. M is LCM. C we have taken another number, another positive integer. So C by M equals to C by M equals to AD by B. AD by B. In place of M we have written AD by B. Now C AD by B or AD by D? AB by D. Sorry, I have written something wrong here. AB by D. AB by D. Now multiplications, D will be multiplied C by AB. So CD by AB. C in place of D. In place of D, D equals to AX plus BY. In place of D, let us write AX plus BY. And AB is as it is. Now after that, what we are doing? CAX plus CBY by AB. Now separately, CAX by AB, CBY by AB. AA cancel, BB cancel. What we have got? C by B X, C by A Y. C by B X, C by A Y. This one we can write shortly. C by B is any integer, C by A is any integer. There is written MX plus MY. MX plus, okay, not M, U and B. UX plus BY. UX plus BY. What is U? C by B. What is B? C by A. UX plus, which is an integer. So look here. What is there that side? C by M. C by M is equal to UX plus BY. Okay. So C is equal to M into something. C equals to MP, suppose. If C equals to MP, then M divides C. Is it not? If A equals to BR, so B divides A, that you got already. So C equals to M something, so M divides C. That is M divides C. Thus M and C are both common positive multiple of A and B, and M divides C. M is so okay. So LCM of AB will be M. M is LCM. So AB by this one. So this one just cross multiplication only. This one you can understand yourself. Just you will write yourself. You will write yourself and you will do the calculation. Then you will understand. Example number 1. Okay. Example number 1. Okay. For today it is okay. So till this much I hope you understand. So in the next video I will start from example number 1. Till then, have a good day.